I've got not too long to go in that chapter. Then we'll roll into the next chapter. So last time we got into Lewis structures, and again how to draw Lewis structures for covalently bonded substances. Remember, as we talked about, there's really several steps that you want to follow. And if you follow those steps, it should lead you to a pretty good structure when it's all said and done. Um, you do not want to do it, as we kind of talked about last time, in sort of piecework where you kind of take each element by itself and try to figure out how the electrons all come together. So just to review some of those steps, obviously you want to think about how it is put together. And remember that to help you sort of decide where everybody should go, you want really the least electronegative element in the central atom. Still, excuse me. So that means that we obviously will not have fluorine in the center, as that is the most electronegative atom. And as we talked about a number of times, that means no hydrogen or fluorine, right? And again, the reason we don't put hydrogen in the middle is what will happen? What will happen if we put hydrogen in the middle there? Yeah, we'll have way too many electrons, right? So we could only have 2 electrons only. Hydrogen, as we talked about, should always be on the outside. Again, never in the middle. Otherwise, it will definitely end up with too many electrons. Again, should look like that. Once you sort of have the logical arrangement, probably the most important thing is to really count up the total number of valence electrons. And that's in the entire molecule. And that number does need to be adjusted if you're drawing something that has a charge, right? So if you have something that has a negative charge, that means that it has gained electrons. So you do need to add that to your total. Otherwise, you'll be short some electrons. And also, if something has a positive charge, you need to subtract that from your total. Again, otherwise, you'll have too many electrons. That number, probably the most important thing when you do a Lewis structure, is that actual number, because when your picture is all said and done, you pretty much got to hit that number on the nose. You can't have any more, you can't have any less. Once you've done that, really the next step you want to do is just arrange your elements. I would say, as we talked about, in most cases, for our purposes here, you'll probably have one central atom in the middle and everything else will be attached. So remember as well, the other thing we want to avoid is a very common mistake that people make, which is they want to like double bond, right, and triple bond right out of the box when they're drawing these Lewis structures. So the next thing you want to do is just, again, a single bond to each of the outside atoms. Remember that each of those bonds represents 2 electrons. You want to count up how many electrons you just used, and you want to subtract it off from your total. And then whatever electrons are left over at that point, remember we always work from the outside in, and they are put on as pairs of electrons. So we'll go around to 4, for example, 6, 8, 10, 12, 14, 16, 18. Remember that everybody on the outside needs 8 electrons. Again, except for our friend hydrogen, should only have 2. If we have filled up all the outside atoms and we still have electrons that we need to put somewhere, then we go to the inside and we put our 2 dots or our pairs of electrons on the center. As we talked about, at that point, you should really be done in terms of electrons if you got into the center atom and you put some dots on there. We always want to make sure that everybody has met the octet rule, except for hydrogen that should only have 2. And if everybody did meet the octet rule, you are good, right? That is a good Lewis structure at that point. You're all said and done. But remember, it's the point here, if you were counting, let's just say hypothetically here, that's why they invented erasers. There goes those electrons. There we go. Now, let's just say hypothetically we were done distributing our electrons. At this point, the guy in the middle there does not have 8. And remember, this is where we want to kind of try to fix that by doing double bonds or triple bonds. And again, that's sort of what you want to think about as you're doing these structures. You kind of want to go single bond and hope that kind of works and fixes everything. Everybody's going to be happy. If it doesn't, then you want to go to your next step, which is double bond. And you want to exhaust all your double bond opportunities. And if that fixes it, good. If it doesn't, then you want to go to kind of triple bond. So once again, we don't want to double bond or triple bond sort of right out of the box, which is a very, very common mistake that people make. Also remember that if somebody is short, we cannot just add electrons, right? Because then we will have too many electrons, and we can't do that because we are restricted by this step in terms of how many electrons that we need. So when we do make something like a double bond, remember that we are taking a pair of electrons in to do so. And what that will do, for example, here is make a double bond on this side. Everybody else will still be single bonded. And now we will have hopefully 8 electrons around everybody, and we will still maintain the same number of electrons. So again, if you follow these sort of steps, it should lead you to a pretty good structure when it's all said and done. Again, you just want to think about the electrons not belonging to anybody in particular. We just want to kind of evenly, as best we can, distribute them to everybody that is there. We then got into sort of geometry after that. And remember, really molecular geometry involves the central atom always. So whenever we're doing molecular geometry, we always want to focus on the center atom. Now, with that being said, obviously there are diatomic molecules that do not have a center atom, and those are, as we talked about, really the easiest geometries to do. Because they are diatomic, they basically only way to arrange 2 atoms is like in a straight line. The geometry is always going to be linear, as we talked about. And again, it doesn't matter if they are 2 of the same atoms, elements there. Doesn't matter if it's double bonded, single bonded, triple bonded. Again, it doesn't matter if they're different elements. The only way you could arrange 2 atoms is basically in a straight line. That's like saying, right, the shortest distance between 2 points is a straight line, and that's always going to be the geometry for it. When we get to like 3 atoms or more, we do have to look at several things, and we do have to look at the central atom when we have 3 or more atoms. And really, we want to look at 2 important things. We want the number of electron pairs, and we want the number of bonds. And based on the electron pairs that are there and based on the bonds, will give us a couple of different geometries that we talked about. The electron pair geometry, which again, I'm still abbreviating as EG, and the molecular geometry, MG, which is the shape. And remember, for us in here, you will be responsible for the shape and not so much the electron pair geometry, but in lab, they go over that as well. So we're just going to talk about it here. Now, the really important thing that we talked about with geometry is probably the most important thing, which is when you're doing geometry, pretty much everything counts as 1. And what I mean by that is when you're looking at electron pairs, if you got dots, if you got a single bond, if you got a double bond, if you got the triple bond, everybody pretty much counts as 1. That also goes for bonds as well. So when you're counting bonds, if you got a single bond, a double bond, or a triple bond, one more there for triple, also counts as 1. So when we're specifically only doing geometry, that is sort of how we count electron pairs, and that's also how we count bonds. So we went through a number of geometries last time. We had something with like 2 electron pairs and 2 bonds. And if we look at that, let me just erase over here. It's got somewhere to scribble. So if we had something such as this, again, always want to focus on that center atom. And again, 1 electron pair, 2 electron pairs, and 1 and 2 bonds. The electron pair geometry is linear, and the molecular geometry is also going to be linear here. Again, as we talked about last time, those electrons that are present are only bonding electrons, right? And the idea behind this geometry is electrons don't want to be near each other because they're both negatively charged, right? So they're going to try to move away as far as possible from one another to find a happy medium and get as far as possible from each other. So in this case, they're going to go on opposite ends of each other, about 180 degrees. And because those are bonded electrons, the atoms move exactly with those electron pairs because they're kind of attached there, and they end up with the same sort of geometry. We also saw 3 electron pairs and 3 bonds. That is what is known as trigonal planar for the electron pair geometry, and trigonal planar there for our molecular geometry. Again, just a quick sort of sketch of that. Looks something like this. Again, looking at the central atom, 1 electron pair, 2 and 3 electron pairs, 1, 2, and 3 bonds. This is also sometimes referred to as triangular because kind of makes an equilateral sort of triangle sort of geometry that occurs in that case. They end up getting away from each other at about a bond angle of 120 degrees. Because we have that extra bond in this case, they got to keep the distance from everybody. So they can't just go opposites of each other. They got that third bond to kind of contend with, and they end up in this sort of triangle type shape. We also talked about 4 electron pairs and 4 bonds. That is tetrahedral and tetrahedral for both geometries here. And again, that would look something like this. And again, 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs, 1, 2, 3, and 4 bonds. Now, again, in this case, we have that 4th bond. So remember, everybody is trying the best they can to kind of keep away from each other. And again, they're going to end up in this tetrahedral arrangement, which has a bond angle of about 109.5. Up until this point, as we talked about, both of the electron pair geometry name and the molecular geometry name are the same because they are all bonding electrons. So again, as those bonding electrons move, so do the atoms, and they basically end up with the same shape as how the electrons are arranged as how the atoms are. It's only when, as we were talking about there at the very end, when we incorporate non-bonding electrons into the fold, that we start to get a different name for the molecular geometry. And that is because, as we talked about, sort of the best situation for electrons is where we have bonding electrons near bonding electrons, so kind of lines near lines. The next best situation, starting to get worse, is where we have non-bonding electrons near bonding electrons, so dots near lines. Also gets worse because there's not an actual atom there, right? So it gives it a little bit more room to kind of move and get away from each other, and that's going to cause the geometry shape to actually change. Remember, the worst repulsion situation in electrons is dots near dots, or non-bonding electrons near non-bonding electrons. They definitely want to try to get as far away as possible. So we saw 3 electron pairs and 2 bonds. Remember that this name here, the electron geometry, is based on the electron pairs, which is trigonal planar. And again, because we had that non-bonding electron, we have angular, or again, sometimes people do call this bent, as we talked about as well. And again, the one that we looked at, maybe I'll just sketch it over here. Something like SO2 here. Just looks something like that. And again, what's going to happen is we have these non-bonding electrons, non-bonding and bonding electrons, definitely trying to get away from each other. Also on this side. But again, these guys can't get too close to each other because also they don't really want to be right on top of each other either. So again, we get that angular or sort of bent shape that occurs in that particular case. We finished there with 4 electron pairs and 3 bonds. Again, 4 electron pairs is tetrahedral, and the molecular geometry is trigonal pyramid. And remember, in this case, something like NH3 that we saw. Also, again, has those non-bonding electrons. So again, going to try to get away. This guy now has that kind of extra hydrogen there, so they got to kind of keep some distance, and it gets you that trigonal pyramidal type shape. And remember, this is the one we talked about before we left, which was there is a difference, right, between trigonal planar and trigonal pyramid in terms of how many electron pairs and bonds. So again, on a quiz or exam or something like that, like we were talking about, you do have to specify. You cannot just say trigonal. You got to actually, make your decision there. And remember, decision like fully saying what it is, not, again, my favorite answer, which is just like, it's like pyramid, planar. Can't you clearly see I got the P on there for something? So it's got to be pretty close. Any questions on that so far? Or anything we talked about last time? Okay, so we have actually just one more sort of geometry to add to our list, and let's talk about that one. And this is water. So again, if we draw our Lewis structure here for water, looks something like this. Once again, we want to always focus on the center atom. So if we go to the center atom, how many electron pairs do I have around that center atom? How many electron pairs are around the oxygen? It is 4, right? Remember that when we're counting electron pairs, it doesn't matter if they're lines, it doesn't matter if they're dots. We just want the total number of electron pairs. So we got 1, 2, 3, and 4 electron pairs happening here. So 4 electron pairs, again, in terms of the electron geometry, is still tetrahedral. But in this case, we actually only have how many bonds? We have only 2 bonds, right? So we got 1 and 2 bonds right there. So what's going to happen here is, in the case of water, we have pretty much all the electron interaction you could ever want. We have, if we just sort of look at it, we have our non-bonding electrons and our non-bonding electrons, which definitely want to get away from each other. We also have our bonding electrons and non-bonding electrons, which also want to get away from each other. Those are the 2 worst sort of interactions. But again, these hydrogens cannot get too close to each other because there are still bonding electrons near bonding electrons. And it ends up, again, as these sort of non-bonding electrons go this way, our hydrogens sort of fold down, and then we get this geometry shape for water, which is known as bent or V-shaped. And it has a bond angle of less than 109.5. And again, that is why what we talked about previously, that we will be going with kind of angular for that previous one. There is a difference in sort of how many electron pairs are present and the actual bond angle that you see. Again, with that angular one, it is closer to 120, a little less than 120. With this one, it's less than 109.5. So there is a difference in terms of what is there. As I mentioned before, though, books and online homework and stuff will still sometimes call angular bent or bent angular. So I'm okay with that, but for here, we'll try to stick with angular for that one to distinguish it between this geometry as well. Any questions on that there? So here's a table similar to what you got in your book there. And again, this is really sort of the best way to think about geometry. As I mentioned before, a lot of people, myself included, it's hard to sort of visualize 3-dimensionally sort of what's going on. So you want to really keep it as simple as possible, which is always go to the center atom, count up all the electron pairs that are present, how many bonds there are, and that will correlate to a geometry. So again, total number of electron groups, number of bonds basically, and our molecular geometry name there, which I was on this table. There it is right there. Our name. Any questions on geometry here? All right, the last thing we're going to talk about in this chapter is actually molecular polarity. Now we talked about drawing Lewis structures. We talked about the geometry, sort of how they're arranged in three-dimensional space. We're going to finish up here talking about molecular polarity. Now, we've talked about polarity a little bit earlier on in this chapter, and that is sometimes referred to as bond polarity. And bond polarity is where we did, if you remember, our difference in electronegativity values. So we used our electronegativity values, right? And we subtracted the two values, and we had those ranges like 0 to 0.4. It's nonpolar, which means equal sharing of electrons. We had above 0.4, so like 0.5 to less than 2. That means they're going to have a polar bond, unequal sharing electrons. And we can go above 2 is typically ionic. But as we also talked about, we really don't need that, because to know it's ionic, it needs to be a combination, right, of a metal and a non-metal, right? So as soon as you know that, you know it's going to be an ionic bond in this particular case. So when we talk about molecular polarity, we're actually talking about the entire molecule as a whole with all the bonds that are present. Is the molecule basically sharing electrons equally overall, or is it sharing it unequally? Now, the bond polarity and the molecular polarity do not always necessarily agree. There is only one place where they definitely will agree, which is pretty much the easiest polarity that you could actually figure out in terms of molecular polarity, and that is diatomic molecules. And if we look at diatomic molecules, we basically only have obviously two things that are bound to each other. So if we take a look at a couple of examples that we saw throughout this chapter, we look at hydrogen, which if we draw the Lewis structure looks something like that. We look at fluorine, or not fluorine, hydrogen fluoride. Say that again, sorry. We look at fluorine, actually, I was correct there. There we go. And if we look at these guys, we can look at sort of our bond polarity in this case. And if we look at our bond polarity between these two guys, we will know that we have either a polar bond or a nonpolar bond. Again, if you had to take a guess based on what we talked about, would the bond in H2 there, hydrogen, would it be polar or nonpolar? What do you think? It will be nonpolar. The electrons are going to be shared equally. They both basically have the exact same electronegativity value, which means the difference is 0, right? And we talked about that being basically a pure covalent bond, perfectly nonpolar. Same thing with fluorine. They both have a value from that table of 4. So if we take the difference in electronegativity, that also is going to be 0 by just simply subtracting the two numbers, basically, right? And that also is going to mean that it's going to share it equally. Because these bonds are going to be shared equally, this guy over here has a nonpolar bond. And this guy over here also has a nonpolar bond. So each of these molecules have nonpolar bonds. So when we look at each of these molecules, how many total bonds are there in each of them? There's only one. And if that one bond is nonpolar, that means that the entire molecule is going to be nonpolar as well. So they will agree with each other. This would be a nonpolar molecule. And this guy would also be a nonpolar molecule. So here the bond polarity and the molecular polarity would be the same, because basically in this molecule, there's only one bond. So whatever that bond is will be what the molecular polarity will be. Question on that there. Okay. Now, again, just like we saw earlier, HF, the bond between hydrogen and fluorine, is polar or nonpolar? It is polar. If you did the difference in electronegativity, I'm going off the top of my head, something like 1.9, which is just below 2, definitely above 0.4, and that's going to be a polar bond. Remember, because this is a polar bond, we could shoot a dipole arrow heading in the direction of the one that is more electronegative. Remember, it always points to the one that's more negative in the bond, And again, the back end that kind of makes like a plus sign is to the side that is more positive there in the bond. So this bond here is a polar bond. And just like the top examples there, this molecule only has one bond, which means if that one bond is polar, this molecule will also be a polar molecule. And this arrow is sometimes referred to as a dipole moment. And they actually use the same sort of arrow that we use for bond dipoles. A dipole moment means that you only have that in a polar molecule. It means that one end of that polar molecule is more negative. The other end of the molecule is going to be more positive. So in this case, the fluorine end is going to be more negative, and the hydrogen end here is going to be more positive in this case. So these are probably the simplest ones that you could figure molecular polarity from, which is these diatomic molecules. Again, all you have to determine in this case is that bond polar or nonpolar? And because it only has that one bond, that will also be the molecular polarity of it as well. Any questions on that there? Now, it'd be great if everything was that simple, but unfortunately it's not. So when we get into molecules that actually have 3 or more atoms present, we actually have to look at a couple of different things. So let's talk a little bit about what we need to look at here. So when we have 3 or more atoms, we want to look at pretty much, are there polar bonds? So that's one of the main things that you need to look at to determine if there are polar bonds in the molecule. If there are no polar bonds, probably a good chance that the molecule is going to be nonpolar, right? So if there are polar bonds, though, you do need to look at a second thing, which is the molecular geometry. So not the electron pair geometry, but the actual molecular geometry are the shape. So let's take a very common example, which is carbon dioxide. If we draw this Lewis structure, the first question we want to know is, does carbon dioxide have polar bonds? Is the bond between carbon and oxygen polar or nonpolar? What do you think? Got a 50-50 chance. What do you think? It is polar. The reason we do know that is we could just use the general trend in electronegativity, right? We see carbon and we see oxygen, period, on the periodic table, and oxygen is further to the right, which means it's going to be more electronegative, and that will create a polar bond between those two, where the arrow, for example, would be pointing towards the oxygen side. So it would point this way, and we would also have a polar bond that is going that way. So in this particular case, we definitely have polar bonds in this molecule. So you may be thinking that it has polar bonds. This actual molecule should be polar. And you do need to look at the second thing in this case. So we could kind of check that off. We do need to look at the actual geometry here. What is the geometry of this, the molecular geometry of this guy? Central atom has how many electron pairs? It has 2, 1 and 2. Remember, when you're doing geometry, everybody counts as 1. Yeah, so everybody counts as 1. So 2 electron pairs. In terms of bonds, we have also 1 and 2 bonds. So this geometry is linear. It is basically 2 and 2 off of our list there. It is basically a straight line. So what we have is, like my pen here, my linear CO2. And what we basically have is oxygen on the right-hand side, pulling this way. Then we have oxygen on the left-hand side, pulling back the other way. I am actually pulling really hard in opposite directions here. Is my pen going anywhere? It is not. They actually cancel each other out. It's kind of like tug of war, yeah, with the rope, little flag in the middle. You have people on both ends of the rope pulling equally. The flag is basically just going to stay in the middle, right? Not going to go anywhere. They're going to essentially cancel each other out. So even though something like CO2 does have polar bonds, because of its actual geometry, they actually will cancel each other out. And this is actually a nonpolar molecule. So it's a really good example to illustrate that you absolutely could have a molecule that has polar bonds, but because of its geometries, they may not be polar overall because they may cancel out. Now, if we look at something like water, once again, the bond between hydrogen and oxygen is polar as well. And oxygen being more electronegative are actually going to head in this direction. So once again here, water does have a polar bond, or actually two of them. Now, the geometry of water is the one we just did a second ago. That's going to be our 4 electron pairs and our 2 bonds, which will give us our bent, our V-shaped, which is why, again, it's usually drawn kind of like that, right? When you see water, oftentimes it's drawn like that. Now, in this particular case, you could kind of think of it. I'll do my best with my 2 pens here. So we got something like this, basically, right? Bent or V-shape. We basically got electron density heading this way and this way, almost like they're going to meet up here as like a string, right, up on top. And if you pull the string, you can kind of imagine the whole thing will move, and it will actually become a polar molecule because of that. In this case, the bond dipoles actually add to each other. They actually head in this direction, where the oxygen is actually more negative. The hydrogen part of water is more positive because of that. And this would be a polar molecule. Question on that there. These little bond dipole arrows that I drew, they are vectors, yeah? I woke up in physics once, and I think they said they had direction, they had magnitude. I might have fallen asleep at that point. Then I woke up long enough to know that in some cases, they actually will add to each other. And in other cases, they'll kind of subtract from each other. So, for example, water, you kind of draw the arrows head to tail, and they will add up in that direction, basically. And anytime you have kind of these bond dipoles or vectors heading in equal and opposite directions, they will cancel, kind of like the rope pulling equal and oppositely. Also, if they're heading like right at each other, kind of like a swinging door, right? If you had a swinging door that swings, something on one side, something on the other side pushing equally, door's not going to go anywhere, right? So again, if they're kind of coming at each other, they will also cancel each other out. Nobody in the right mind wants to do vectors, right? So there should be an easier way to do that, and there is. So there's a much easier way that you could do molecular polarity when you have 3 or more atoms, and you probably be right 99.9% of the time, I would think, in most cases. So let's talk about how to do that. There are certain geometries which are referred to as being symmetrical geometries. And for you guys, your symmetrical geometries are trigonal planar and tetrahedral. And these are the molecular geometries that we talked about earlier. So these are the molecular geometries that we're talking about. What these guys have in common are, if you look back, we have no dots on the center atom. So no non-bonding electrons on the central atom, no dots on the central atom. And if you have one of these geometries and all the outside atoms are the same, it will give you a nonpolar molecule, because they will all be pretty much equal distance from each other, pulling in each of the opposite directions. So for example, if we took CF4 here, and I'm not going to draw the electrons on the fluorine, but if we take a look at this, this guy here has polar bonds between the carbon and the fluorine being the most electronegative atom that there is. And so it does have polar bonds, but all of the atoms on the outside are the same. So when I look at this, they have no dots. All the atoms on the outside are the same. This is actually going to be a nonpolar molecule, because even though it has polar bonds, they're going to end up being like the tug-of-war rope, equal and opposite of each other. So they're all going to pull equally. Nobody's going to go anywhere, basically, like on the rope. And they're going to basically cancel each other out. Now, what would happen, though, if I had this exact same setup, but I decided to get rid of a fluorine and replace it with a hydrogen? In this case, we would still have polar bonds. The bond between carbon and hydrogen, polar or nonpolar? It is nonpolar. Remember, that's that 0.4 difference, and reason the organic thing I was talking about earlier, it's actually nonpolar. In this particular case, you got like 3 people on the rope, if you want to think about it, pulling, and this guy not pulling anyway. Yeah, he's actually, believe it or not, kind of going with them a little bit. So you could imagine that that whole thing would kind of move, and this would then be actually a polar molecule. So if you draw a Lewis structure and you look at it, and you look at your central atom and there's no dots on it, and all the outside atoms are the same, go nonpolar. Yeah. If you draw your Lewis structure and there's no dots on the central atom, but all the outside ones are not the same, go polar on that. Yeah. And that's a pretty quick way that you could do that for these symmetrical geometries. Any questions on symmetrical geometry? Yeah.
That's unless they have the same difference on the electronegativity, right? Because we have some elements that have the same.
You do. So the truthful answer is, in that case, you would default back to kind of the first thing there. You got to probably, in most cases, have a polar bond, at least there in most cases. And it kind of depends on the molecule, but you do need to kind of at least have a polar bond somewhere. So if they're all nonpolar, technically speaking, you wouldn't. It would probably be nonpolar, but people might still consider it polar, because even though we talk about it being nonpolar, something like CH4, it's not perfectly nonpolar, right? There is a little bit of, difference there, but not enough to be considered in normal cases polar. So there are, you will come across maybe some of those, not in this class probably, but if you're looking around, there might be a situation like that. It usually will happen a little bit more with non-bonding electrons being present, and that's sort of the issue on that. But yeah, I would say for our class, you need to have at least a polar bond for it to be. Other questions? All right, so let's talk about unsymmetrical geometries. And that's pretty much everybody else that's on that list. So we have our angular, we have our trigonal pyramid, and we have our, not tetrahedral, we have the one I just did there, bent or V-shaped. And what each of these have in common is, if you draw that central atom, you're going to see dots. Yeah. So if you draw your Lewis structure and you see dots, and all the outside atoms are the same, gonna probably be a polar molecule. So you could almost do molecular polarity by dots or no dots, basically, and determine what it's going to be. Is it going to be polar or non-polar? I will say that, to sort of your question, in a situation like this, where you may actually have non-polar bonds, not pure covalent bonds, but non-polar bonds where there's a slight difference in electronegativity, and you have those dots, people will most likely still consider it a polar molecule, because it does have those non-bonding electrons have a little bit of pull as well. So this is a situation where you could have something like that, where you're like, hey, the difference in electronegativity says these are non-polar, but the geometry of it and those non-bonding electrons sort of contribute to keep it kind of slightly polar. Not tremendously polar, but it'll be slightly. Now, what that leaves you in terms of molecular geometry to figure out is probably the easier one, which is linear. Yeah. So linear would be the only one you have to figure out. So if you have something that is linear and everybody's heading in opposite directions, like we talked about, it's going to be nonpolar. If you have linear and everybody's heading towards each other, it's also going to be nonpolar. It is possible though to have linear where everybody is heading in the same direction, and then that would be polar in that case. So again, kind of same idea if you think about the rope example, right? If one person's pulling this way and the other guy's like, cool, I'll pull that way with you, right? The whole thing's going to move, right? So everything's going to kind of move with it. Any questions on that there? Yeah. For our class, you probably don't need to draw the arrows, but those are usually what are sort of drawn to represent. And by the way, the arrows, those dipole arrows are only drawn for things that are polar. So if it's a polar molecule, they'll have a dipole moment, which is, this arrow sort of drawn. If you're talking about bond polarity, it's usually that difference in electronegativity just between these two atoms, how they're being shared. But when you talk about dipole moment, you do that. You probably want to worry about drawing too much of those arrows right here, but in books and stuff, they'll sometimes show them, and just so you know what they sort of are. Now let's take a look at some examples and see how fast we can do this, because we're busy people. We don't have a lot of time. All right, let's go here. Top left. I want to go dots or no dots. On the central atom, always looks central, right? Dots or no dots? No dots. Is everything on the outside the same or different? They are different. They're not all the same element, right? That means that this guy is going to be polar because this guy has a polar bond, the other ones don't. He's going to pull away basically the rope. This one, we look right here, central atom, dots or no dots? No dots. Is everything on the outside the same? Polar or non-polar? Non-polar. Everybody on the outside is the same, right? Symmetrical geometry. Central atom, dots or no dots? Dots. Everybody on the outside the same? Yes, polar or non-polar? Going to be polar. So again, if you have dots, everybody's the same, polar. If you have no dots, everybody's the same, non-polar. If you have no dots and everybody's not the same, polar. Yeah. So that brings me to here. Polar or non-polar? Dots or no dots? No dots. Is everybody on the outside the same element? So it's going to be polar. Heading in this direction, two chlorines are going to pull way more than the hydrogen in this case. How about this guy? Dots or no dots? Dots. Everybody on the outside the same? Yes. Polar or non-polar? Polar. Yes. Dots. Everybody the same. Polar. Yeah. Dots or no dots? No dots. Everybody on the outside is same. Going to be non-polar. So that is pretty much as quick as you could do it. Dots, no dots. So once again, to summarize, no dots, no dots, all same, going to be non-polar. No dots, different on the outside, going to be polar. Dots, all the same, going to be polar. And again, it's always the one in the middle. Yeah. So you always want to look at the one in the middle. It's always the one you want to look at. Any questions on molecular polarity? All right, that wraps up this chapter. Continue on next chapter, which is chapter 7. It's got a bunch of stuff in there. So we're gonna talk about equations, types of reactions, and then we'll get into some calculations involving reactions. So we're gonna start with equations. So when we look at an equation, there are two parts to an equation. And we always want to make sure that the equation, whenever we're dealing with it, pretty much in chemistry, you always want to make sure that it's balanced. And sometimes equations that you're given are going to be balanced. Sometimes they will not be balanced. I would say probably, again, if you kind of see numbers in the equation in the front there, you're probably a good shot it's balanced. If you see no numbers in the coefficients, which are these numbers in front, then you definitely should take a good look at it to make sure if it's balanced or if you need to balance it. A reaction or equation has two parts. We have our reactants, which are our left-hand side here. That is our starting material in a chemical reaction. And then we have our products, which are on the right-hand side of the arrow. Those are what are formed as a result of the chemical reaction. Remember, in a chemical reaction, the only thing that happens is pretty much all the bonds on the left-hand side, everybody just breaks apart. And then they kind of reassemble there on the product side in new compounds and make new bonds. The only thing that gets played with are electrons, and we don't touch anything in the nucleus, which means we do not touch anything like protons. And I say that because protons are most important because they're the ones that determine the element, right? So we don't touch the protons, which means we have conservation of elements when we do a reaction, a chemical reaction. Like in this case, if we started with 4 hydrogens, we will end with 4 hydrogens. They may just be in a different spot or a different location. And we start with 2 oxygens, we'll end with 2 oxygens. We never lose anybody along the way. We have a conservation of mass is that as well, because the 4 hydrogens on the left weigh pretty much the same as the 4 hydrogens on the right. So the mass of all the reactants will be the mass of all the products along the way. Other things that we typically will see in an equation, we will oftentimes see the states. So little like S written next to formulas, L, G, and AQ. And that is for something being in the solid state, the liquid state, the gas state. That basically is like a water environment. It's really a solution. So like all those solutions used in lab, they're sort of liquid state, they're pretty much aqueous solutions as well. Other things that sometimes end up in an equation, things on top of the arrow are sometimes written. A lot of times a catalyst is added, and sometimes a catalyst may be something like a metal, like platinum. It may be written as H plus, which means it's like an acid as a catalyst. A catalyst is not a reactant. It is not a product. And it does not get used up in the reaction. It is there in most cases to facilitate that reaction happening faster. There are negative catalysts that actually will slow down reactions, but most of the time when people talk about catalysts, they talk about it in the effort of speeding up the reaction. How they do that is not super important for our class, but what they essentially do is find a sort of alternative pathway, a more efficient pathway in terms of energy for that reaction to take place. For example, if you had a piece of metal and you didn't use it as a catalyst, but you have these gas molecules just kind of flying around, the way for them to react is they got to go find each other, right? So they're just flying around trying to hopefully come in contact with each other. So you throw down like maybe a piece of metal catalyst. Now, instead of just randomly flying around, that may attract both of those gas molecules to the metal, and that's going to put them really close to each other. And then they're going to be very close to start reacting a lot quicker, right? Than just having to fly around and try to find each other. So sometimes, a catalyst works that way. It finds really a alternative pathway, a more efficient pathway for that reaction to take place. Ultimately, what your reactants to get over to the products, there's a hill that basically has to climb in terms of energy, and that's the activation energy. And what a catalyst is able to do by finding this alternative pathway is it lowers that hill. So if you just think about a regular hill, if you had to climb a mountain to get to the other side of campus, right? Not a lot of people side, right? If you just had to climb like a speed bump in the parking lot, most people could probably get up and it doesn't take a lot of energy to do so. You'll get up and over that much faster if you had to jump a giant hill, like the hill you drive up, right, when you're trying to go to park in the school, right? If you had to walk that hill versus just like a speed bump, it's going to take you a lot longer to do so. Any questions on that there? No, most of the time it is just in most cases there to facilitate a reaction that would normally take place faster. Yeah, so for example, there's reactions which are sometimes referred to as being spontaneous. And sometimes people, when they hear the word like, hey, this reaction is spontaneous, we think we like snap our fingers and the reaction happens super quick. But when we talk about spontaneous reactions, what we're talking about is under those conditions, if you leave it alone long enough or short enough, it will just happen, is what that means. It has nothing to do with how fast or slow the reaction occurs. Kinetics deals with how fast or slow it is. For example, the formation of ammonia is a spontaneous reaction. But if you do not use a catalyst, you're going to be there all day for that to happen. And so it takes a really long time. So that helps speed it up. But that's sort of, if those two things are never going to react, probably it's not going to help. Other questions? All right. So when we use equations, as I mentioned before, you definitely want to make sure that you are balancing your equations. And when we balance the equations, honestly, there's different methods. So we'll talk about probably the best way. But here are some things that you want to keep in mind as you go to balance the equation. First off, if you happen to be given everything just in words, you need to make sure that you get the right formulas down first. So you want to think about not balancing the equation in that case. You want to think about, do I have the correct formulas? So you want to think about like we did with nomenclature. You want to get all the right formulas down first. If you do not start with the right formulas, you're going to be there all day trying to balance something that will never balance. And then you should balance it. So that should always be the order at which you do that, is correct formulas and then balance. Oftentimes this happens where, for example, you may just be given reactants and you're asked to like write the formula of the products. And what people often do is they try to balance and write the formulas at the same time, and they end up with wrong formulas that, again, will never balance. So always want to go in that order. Forget about the balancing part first off. Just make sure you're starting with everybody's correct formula, like you were doing naming and writing formulas. You got everybody down. Then you go back and balance. We balance equations only by changing coefficients. Those are the numbers that come in front. So when we have something, we only change our put numbers in front. We never ever change anything that's a subscript. That's a no-no, yeah? So don't do that. Why would I not want to, if I had, say, something like water, decide to change this number? Is it still water at that point? It's not. You just change what it is. So only the numbers that come in front is the only numbers that you could put in there. Also, don't do any weird things I've seen before where people decide, well, I'm just going to kind of put like a big number in between as well to help that oxygen out. That not good either, right? So you don't want to do any of that. So only the numbers in front. Honestly, sometimes people say start with the most complicated. I personally would start with what looks the easiest to balance. So whatever I could look at and see what's the easiest to balance, that's probably a good move. You want to keep putting coefficients down, and it may require you to put one on the left-hand side, then go to the right-hand side, back to the left-hand side, back to the right-hand side, because as you are balancing equations, you're going to screw up the balancing, and it's not going to be balanced. You'll fix one thing and then kind of mess up something else. So eventually, though, if you do it correctly, everybody should fall into place, and you should end up with the exact same number of elements on each side of the arrow, and then you'll have your balanced equation. The one main thing that you have to look for when you're balancing an equation is all of the coefficients. They all need to be whole numbers. All the coefficients. They actually need to be the simplest set of whole numbers. So what do I mean by that? I mean that if you have this equation, A plus B goes to C, I know my alphabet, that's good. And let's just say it was balanced with, say, these numbers here. So I got this equation balanced. I laid up a 4, a 2, and a 6. What can I do with all those numbers? Divide them all by 2 and still have a whole number. And this would not be the properly balanced equation. You actually would need to go through and divide everybody by 2. and get this equation, which would be the properly balanced equation. And that happens because sometimes people may see bigger numbers to balance it, and it's absolutely balanced. You have the same numbers on each side, but to be properly balanced, all those coefficients has to be whole numbers, and they has to be the simplest set of whole numbers. So if you look at all your coefficients and you could divide everybody by a number and still get a whole number for everybody, then you should do that. If not, if you could divide everybody and you get like 3 of 4 whole numbers, then you should leave it alone because you got all has to be whole numbers. So if you can't reduce down everybody, then you should leave it alone. But if you can, you should reduce it down. Any questions on that there? All right. So let's take a look at how I would approach an equation like this. So the first thing I like to do, to be honest with you, is I like to make a table. Yeah. So I have reactant side, I have product side, and I have a line in the middle, which I don't want. So let me get rid of that first. All right, get rid of that there. All right, and I have some elements. So I have nitrogen, oxygen, and hydrogen. And I just like to make a little table to just see what I'm starting with, right? So on the left-hand side, how many nitrogens do I have? I got 1 right there, right? On the right-hand side, I have 2, right? The 2 on the bottom counts for 2 of them. Left-hand side, I have 1 oxygen right there. Right-hand side, I have 1 oxygen right there. Left-hand side, I have 2 hydrogens right there. And our left-hand side, right-hand side, I also have 2 hydrogens right there as well. Now, this table helps me because it maybe organizes for you. It also gives you maybe an idea as to where to start, right? So clearly by looking at this table, hydrogen and oxygen, we're good, right? They're balanced. So that to me tells me I probably should start with the nitrogen, right? So that would make the most sense. Now remember, to balance the equation, it is only the coefficients. So I'm going to go to the left-hand side of the equation, bless you, and put a 2 in front of it. When I put the 2 in front, it does count for everybody behind it. So this 2 counts for the nitrogen and also the oxygen that's behind there. By the way, if either of those had a little number on the bottom, you would have to multiply it as well to figure out how many total you got going on. So now I'm going to redo my table here. I now have 2 nitrogens. I now have 2 oxygens, and I still have 2 hydrogens. Much like what always happens when you balance an equation, you fix one thing and kind of mess up something else. So my table probably points me in the direction of oxygen would be next. It's the only thing at this point that's not balanced. And again, I got 2 oxygens on the left, but only 1 on the right. So I could fix that by putting a 2 in front of where the oxygen's at. Once again, this 2 is going to count for this guy and that guy behind it. And that will give me 2 nitrogens on the right. 2 times 1 is 2 oxygens. 2 times 2 for the hydrogen is 4. So again, you do need to multiply the coefficient by the subscript, a little number, if you have something in front. That clearly means I'm almost there, right? The last thing I should balance is the hydrogen that's on the left, right? So in this case, I need to get it to 4, so a 2 right there should do it. That will give me 2 nitrogens, 2 oxygens. Once again, 2 times 2 is 4. I am now balanced with my equation. I have the exact same numbers of these elements on each side of the equation. So again, you don't have to use a table, but sometimes it's very helpful to kind of organize everything and kind of keep track of where everybody's at rather than just kind of looking at and throwing down numbers. Any questions on that there? All right, I tried one, you try one. Let's see. All right, balance this. Okay, so let's take a look and see how you're doing. So once again, I'm going to make a table of all my elements here. I got carbon, hydrogen, oxygen. So on the left-hand side, which is our reactant side, we have 3 carbons. On the right-hand side, we have just 1. Left-hand side, we have 8 hydrogens. Right-hand side, we got 2 hydrogens. Left-hand side, we have 2 oxygens. Right-hand side, how many oxygens do I have? I do have 3. I have 2 here plus 1 more over here, right? So we're totaling up everybody on each side, and that would give me 3 oxygens. At this point, really nothing's balanced. So frankly, to me, I think carbon would be pretty easy to balance. I think also you could start with hydrogen as well. Why would I perhaps not want to start with oxygen? On the right-hand side, how many places does oxygen reside? 2 different places on the right, right? And on the left-hand side, only 1 place, right? So if you start playing with oxygen first, and you're also going to mess up those other guys, right? And you're not going to probably balance. So you want to maybe save that towards the end. Start with it 1 side, 1 place on each side. So I'm going to go with carbon first. To fix carbon, I'm going to put a 3 again in front to do so. That is going to go to everybody behind it. And that means that now I have 3 carbons. For my hydrogen, I still have 2. Now, in terms of oxygen, in the first guy on the right here, I have 3 times 2, which is 6. And I still got the 1 hanging out over here. And that's going to get me to 7 at this point, right? Once again, I'm going to leave oxygen because hydrogen 1 in each side, right? So much easier to fix. So to fix the hydrogen at this point, I got 8 on the left and 2 on the right. So I need to put a 4 in front of it. Again, that's going to go to everybody behind it as well. So we still got our 3 carbons. Hydrogen, we now have 4 times 2, which is 8. Oxygen, we are now still with 6 here, but we now have 4 times 1 over here, which is 4, right? So 6 and 4 is 10. Now that's going to make oxygen probably pretty easy to balance because all I have to do now is go to the left and put a 5. And I will still have 3 carbons, 8 hydrogens, 5 times 2 is 10. Yeah. So again, I would recommend if you got something like oxygen and multiple things, maybe just kind of leave it towards the end and try to fix out the other ones. And it might make it easier there when it's all said and done. Question on that one there. All right, let's try. Okay, so let's take a look. Once again, I'm going to make my table here. So on the left-hand side, I got 2 borons. Right-hand side, I got 1. Left-hand side, in terms of oxygen, I got 3 here. And again, I got 1 more over there. So that is going to be 4. Now on the right-hand side, how many oxygens do I have? I do have 3. This 3 does get distributed to everybody in the parentheses. So I do have 3 oxygens. Hydrogen, I got 2. And also, again, distributing that 3 to the hydrogen on the right will give me 3. So if you do have parentheses and a number on the bottom there, you do have to kind of multiply it into everybody inside the parentheses. In this case, everybody inside the parentheses is 1, but if they did have a subscript, you would have to multiply it by that subscript on the bottom as well. Not a lot to work with here, so I'm just going to go right-hand side because that's pretty much going to do everybody, I think. So might as well again start with what seems simple, which would be the boron, right? I could easily fix the boron by putting a 2 in front, right? Now, when I put that 2 in front, it still goes for everybody behind. It goes for this guy. It also goes for who's in the parentheses as well. So that's going to give me 2 borons. Now for the oxygen, we already have basically 3 times 1 for the parentheses. Then we need to times it by 2 for the outside coefficient. So that's going to get me a 6 basically, yeah. Same thing for the hydrogen. We basically have 3 times 1 for what's inside. And then that 3 times the 2 on the outside will give us 6 as well. So you kind of have to, in this case, multiply in and then multiply out to the coefficient as well to get the right number. Again, basically, because what that means is when with the parentheses of the OH3, it basically means you basically got 3 of those, right? So if you just count it up, you got 3 oxygens and 3 hydrogens. Now, when you put the 2 in front, you now got double of it, right? So now you're at that point, and then you got another 3 oxygens and 3 hydrogens, which gives you your 6s on each of those. Yeah. So again, you have to kind of multiply in and multiply out as well. All right. So clearly at this point, we fixed the boron. Nothing else is fixed over there on the left. We do not want to do anything with the right-hand side at this point, right? Because you do not want to get into the vicious cycle of erasing numbers and putting new numbers, erasing numbers, putting new numbers, yes? So you feel good about the first number, leave it until you absolutely maybe have to erase it. So we definitely want to go to the left-hand side. That's going to leave me 2 options in terms of elements, right? I got hydrogen and oxygen. Which one do you think I'm going to go for first? I'm going to go for hydrogen or oxygen. I'm going to go for the hydrogen because I see oxygen over here in 2 places, right? I see hydrogen only in 1. So that's going to be much easier to balance, right? I just got to go to 1 location and balance it up. So that's why I'm going to go with hydrogen first in this case. Now I need to balance it. I got 6 on the right, 2 on the left. I'm going to put a 3 in front there to balance my hydrogen. That's going to give me 2 for the boron. Once again, this 3 goes for everybody behind it. Now, in terms of oxygen, I have 3 right here, and 3 times 1 is 3, right? So that gives me a total of 6. By balancing the hydrogen, it also fixed the oxygen, yeah? And 3 times 2 would give me 6, and now I am balanced. So again, if you got something in multiple places, leave it for the end. Yeah, you might get lucky like we just did here. Fix one thing, fixes other things, and that's very common in balancing. Sometimes you fix one thing, it'll just kind of work everybody else into place as well. Question on that one there. All right. Rolling through here. Let us do this one. Okay, let's take a look and see how you're doing on this particular one. We're going to do our table here. So on the left-hand side, we got a 1 nitrogen. Right-hand side got 1 nitrogen. Left-hand side, 3 hydrogens. 2 hydrogens on the right. Left-hand side, 2 oxygens. Right-hand side, we got 1 oxygen there, right? And we got 1 more there, which also looks like a 2. So here in this case, everything looks good except for our hydrogen. We actually have 3 on one side and 2 on the other. We need like a common number there. If we take 3 times 2, that is 6. So in this case, we're actually going to put a number on each side to try to get those guys to 6. So to get my hydrogen on the left to 6, I would need to put a 2. And to get my hydrogen to 6 on the right, I would need a 3. Once again, like before, these will go to everybody behind it as well. So let's add up and see what we got going on. Now for nitrogen, we got 2. For hydrogen, we have 2 times 3, which is 6. We still have 2 oxygens. On the right-hand side, we have 1 nitrogen still. Hydrogen, 3 times 2, which is 6. Now, in terms of the oxygen, we got 1 there. And we got 3 times 1 here, which is 3. So we're up to 4. So much like what happens, you fix one thing and pretty much mess up everybody else. So again, at this point, I'm going to go with what seems the easiest to balance between nitrogen and oxygen. Which one seems the easiest? Nitrogen, yeah, 1 on each side, yeah. So I'm going to go for nitrogen next. I got 2 on the left and 1 on the right. So we're going to put a 2 there. That's going to go here and here. That's going to give me 2 nitrogens. Now in terms of hydrogen, still 6. Oxygen, now I have 2 over here and 3. That is now 5 at this point, yeah. I got everybody balanced except for the oxygen. Clearly, I got coefficients residing everywhere except the O2. Again, at this point, we're not going to erase things because we don't want to maybe go backwards. So clearly, at this point, we should just go to the next problem because this one not good, right? I think at this point. So basically here, we do need to balance it. We do need to turn basically our 2 on the left-hand side into a 5 to balance it, right? And you could do that a couple of ways, but one way you could do it is you could actually use a fraction to do so. And if I take, say, 5 up on top and 2 on the bottom, and I look and see what I got, I now have 2 nitrogens. I now have still 6 hydrogens. When I take 5 divided by 2 times 2, the 2's cancel and I end up with 5, which is what I'm looking for, yeah? Can I leave it like that? No, because at the beginning we said all the coefficients need to be whole numbers. So you absolutely positively can use a fraction to balance an equation. Sometimes you need to do that where you have, like, say, molecular oxygen or nitrogen, and like that oxygen or nitrogen, a couple things on their side. But you do need to clear the fraction. So to clear a fraction, we need to multiply everybody by the denominator. I think they call that on the bottom. In this case, it is going to be multiplied by 2. Again, everybody needs to be multiplied by 2, not just the fraction. So I got to multiply everybody. If I do that, I will end up with 4NH3 plus 5O2 goes to 4NO plus 6H2O. And if I didn't screw anything up, we actually should still be balanced. So let's take a look. I got 4 nitrogens on the left. I have 4 on the right. I have 4 times 3, which is 12 hydrogens there. 6 times 2 is 12 hydrogens there. 5 times 2 is 10 oxygens. I have 4 times 1, which is 4. 6 times 1, which is 6. 6 plus 4 is 10. I am balanced. So you can use a fraction to balance the equation, but you do need to clear it. How do you know what fraction you should use? There's a very simple formula. When you go to use your fraction, top number is always the number you need. So if you remember in this equation here, we needed 5, which is why we put 5 up on top. Bottom part of the fraction should match the subscript, which is that small number. And if you look here, subscript is 2. So that's why those guys match. Top number is the number you need, and you always pick the right fraction in that case. So that's a good way to remember what fraction you should maybe use. Any questions on that? Do you have to use a fraction all the time? No, but there definitely is going to be times where you might need to use a fraction. Could you have done it by just figuring out the bigger numbers? Yeah. But again, sometimes it might be easier to kind of do that, especially if that's the only thing left. Put the fraction and then clear it, and you'll get the numbers that you need. Question on that there. All right, let's talk about a couple other balancing things here before we move on. Let's take a look at this one here. And when we look at this one here, there's a lot going on. There is a lot of polyatomic ions in these guys. And if you look at it, you hopefully should recognize some of these. We got some carbonate, a little sulfate for the evening. And when we look at these polyatomic ions, I got carbonate there and there. I got sulfate there and there. Could you do the balancing exactly the way we've been doing it, which is element by element, and do a table? The answer is yes, you could. There is just going to be a lot more multiplying in and multiplying out that you'll have to do, and probably a little bit more room for an error that might occur. So when you have an equation where you can recognize some polyatomic ions on each side, you should think about maybe just keeping them together and balancing them as like units. Like I got this many carbonates on the left and this many carbonates on the right. And instead of thinking about carbon and oxygen separately, keep them together and balance them. So to show you how this goes, in this case, we actually have two different polyatomic ions. You could actually choose either one. One may work better than the other. And if it doesn't work great the first time, just switch to the other polyatomic ion. So for example, if I decided I wanted to fix the, I don't know, we'll go with the sulfate first. Okay, so when I look at the sulfate here, I have one sulfate on the left-hand side, right? And I look at the sulfate on the right-hand side. How many do I have? I have two, right? The coefficient or the subscript on the outside. So to fix the sulfate on the left, all I have to do is put a 2 in front of it, right? And that's going to give me the two sulfates that I need. Now, when you do this method, what you should do is once you put the coefficient to fix the polyatomic ion, the next place you should go is whatever elements with it, right? So in this case, that also changed the sodium to 4, right? 2 times 2, which is 4 on the left. When I look at the sodium on the right, how many do I have? So I need to fix that. So to fix that, I need to put a 2. That then gives me the 4 sodium I need. That also affects the carbonate. How many carbonates do I have now? Total carbonate units I have 2 CO3 units. How many CO3 units do I have on the left? We're good, yes. Nickel's good as well. Everything falls into place. So it is much easier. Take a moment and look. It is good. Trust me. It is much easier when you have these polyatomic ions to kind of keep them as whole units and balance those units. And what you want to do is what I just did there. You want to go and balance the first polyatomic ion, and then whatever that's attached to on that side, that's where you should go next. And then whatever that's attached to, that's where you should go next. And eventually everything will fall into place. You could, again, like I said, go element by element, but it's going to be probably a lot more work with all those parentheses and multiplying in and multiplying out. So it's much easier to sort of do that thing. Question on that there. All right, let's get some practice here. Try some of that. Okay, so let's take a look, see how you're doing. So once again, if we look at the first one, it is pretty much littered with some of these polyatomic ions. So again, this would be a case where I'd want to kind of keep everybody together and balance them. You do have a choice as to which polyatomic ion you want to start with. And like I said, sometimes one will work better than the other, and one really won't work so great to do this method. But in this particular case, I'm going to personally go with the sulfate. And the reason I'm going to go with the sulfate is when I look at the nitrate on the left, I have 2 of them, right? And I look at the nitrate on the right, I have 3. That's going to require me to put coefficients on both sides to start with, right? So it's a little bit more complicated. So maybe I don't want to do that. If I look at the sulfate on the left, I have 3 and I have 1, that's only going to require me to kind of do 1 coefficient to start with, which again might make it a little bit more manageable. In this case, the other way will also work out, but it's just a little bit more numbers to kind of work with. So by doing that, I'm going to go 3 for my sulfate here. Once again, that's going to fix the sulfate. And again, that tells me the next place I should look is what the sulfate's attached to, which is the calcium. And that is 3 calciums. On the right-hand side, on the left-hand side, I have how many calciums? I have only 1, right? So to fix that, I'm going to put a 3 for the calcium. That 3 will also go for my 2 nitrates, which now give me how many total nitrates? 6. That is where I'm going to go next. So now I'm going to go to the right-hand side. I have 3 nitrates. To fix that, I need to put a 2. And that also affects the iron, which is now 2 on the right and 2 on the left. And we're balanced, yeah, at that point. So again, as you can hopefully see, Much easier to do that. Again, if you chose the other one, you would just have to put coefficients on both sides. And again, it would work out in this case. I will be honest with you, some cases, if you start with one polyatomic ion, you may get into a situation where it doesn't work. So in that case, just go back to the beginning and start with the other one, and then it should work with the other one. Any questions about that? All right, same idea here. We got sulfate and sulfate. We got phosphate and phosphate. Clearly, in this case, we got one sulfate on each side, so I'm not going to play with that at this point because it's balanced. That means I'm going to look at the phosphate. I have one phosphate here and two here. So that's going to put me a 2 right here for my phosphate. That then directly affects the silver, which is now 6. So I go to the right-hand side where silver is currently at 2. To fix that, I need a 3. That gives me now how many sulfates? Gives me 3 sulfate units, which then if I go back to the left, I could easily fix by putting a 3. And that will also fix the copper that I need, and I will be balanced. So again, a lot easier than going element by element, but you could still do the element by element. Again, just a lot more kind of multiplying in, multiplying out. Any questions on polyatomic ions? I would highly recommend just kind of keeping them together to balance them is a good way to do it. Also, faster way, as you can kind of see, it can be done a lot quicker, probably balancing those. Obviously, to do that, you need polyatomic ions. If you don't have an equation with polyatomic ions, you can't really do that method. You then should definitely do probably the table method. And that's the situation we have here on the bottom. We really don't have any polyatomic ions, right? So we're just going to kind of go back to what we did previously, which is make a little table action here. And we got carbon, hydrogen, and oxygen. On the left-hand side, we have 4 carbons. Right-hand side, we have 1. Left-hand side, we got 10 hydrogens. Right-hand side, we got 2. Left-hand side, we have 2 oxygens. And right-hand side, we have 2 oxygens there. And again, we don't want to forget about that one over there, which will get us 3. Once again, in this case, just go with what's simplest. And in my opinion, again, carbon's a really good place to start with. So we got 4 on the left, 1 on the right. That's going to put me a 4 over here for my friend carbon. Going to go to this and the oxygen as well. That's going to give me 4 carbons, still 2 hydrogens. Now for oxygen, I have 4 times 2, which is 8. And I still have the 1 over here, which gets me to 9 at this particular point. Once again, the path of least resistance here is going to be hydrogen. Again, it's in one thing on each side only. So that makes it a little bit simpler to go after next. Again, 10 hydrogens on the left, 2 on the right will require a 5 being put there in front of the hydrogen on the right. That's going to give me 10 hydrogens. We will still have 4 carbons. Now in terms of oxygen, we still have 8 here. And now 5 times 1 is going to be 5. And is that a 13, dare I say? That looks like a 13 in this case, right? Once again, the only place left is to go to my oxygen on the left. This would be a great place to do a fraction, yeah? Because we need to turn basically our 2 into a 13. Again, how we pick the fraction, top number is the number we need, which means up on top should go 13. Bottom number should match that guy, right? So 13 over 2 seems like a winning combination there. That will get me 4 carbons, 10 hydrogens, and again, 13 over 2 times 2 gets you 13, right? First off, question on that there. Do I leave it like that though? I don't. I now need to clear the fraction so I get the properly balanced equation. Once again, we're going to take everybody and multiply by the denominator, right? The 2 in this case. And again, it's not just a fraction, but everybody that's there. That's going to get me 2C4H10 plus 13O2, 8. I'll try that again. 8CO2. Magic ink. And 10 waters. Once again, we should still be balanced, even though I wrote really badly there. On the left-hand side for carbon, I have 8. On the right-hand side, I have 8. For hydrogen, I got 2 times 10 on the left, which is 20. 10 times 2 on the right, which is 20. Oxygen on the left, 13 times 2 is a lot for this late hour, but 26, I hope, yes. And on the right-hand side, we got 8 times 2, which is 16. And we got 10 times 1, which is 10. 16 and 10 is 26. So that does look like a winner there in that case. So again, coefficient-wise, we have a 2, 13, an 8 for the CO2, and a 10 for the H2O. Any questions on how to balance the